Well, hey there. So we're going to start looking at our second set of notes for this week, which is talking about the binomial theorem. We're going to do some calculations that will feel more familiar, as well as some proofs. So as you recall, the binomial theorem, or I hope you recall, is that if you have a binomial to a power, that's the same as the series of n choose k times x to the n minus k times y to the k. Sometimes you'll see it expanded out, such as like if I've got a plus b to the n is the other variable set often used. Well, this is going to be a to the n plus n choose 1, a to the n minus 1b plus n choose 2, and so on, all the way to n choose n minus 1, a, b to the n minus 1, so all the a terms have been depleted, and the b terms are now the ones that are left. Again, hopefully this feels familiar. If it doesn't, if this is something brand new, please, again, don't hesitate to talk to me about it and ask questions. Now, we're going to start with a question that's going to feel familiar to what you're used to seeing with this binomial theorem. Find the coefficient for x to the 6th times y to the 3rd in 3x minus 2y all to the 9th. So what this tells us here is we have our binomial, so we have our term like this. This power is our n, and then the powers on x and y tell us our k. So the power on y in this case will be our k, and 6, this checks out, is n minus k, which 9 minus 3 is in fact 6. So that tells us our first term, because we're going to use n choose k. So 9 choose 3. And then we're going to take our full x and y terms. So this is a common mistake. This is your first term, and then with the negative, this is your second. So your first term is 3x to the 9 minus 3. So that's how we're going to get our x to the 6th. And negative 2y to the k is 3. So make sure that you're including any coefficients on your x and y terms, that your first and second terms. From here, it's straightforward algebra. The numbers get a little bit big, so you will end up using your calculator for a little bit. 9 choose 3, you can do without a calculator, but you end up with 84. This is the one where I think you'd probably want a calculator, because now you have 3 to the 6th for your x to the 6th. And I don't necessarily want to do 3 to the 6th by hand. It is 729. And then negative 2 to the 3rd, that's fine by hand. That's just negative 8. And then you have x cubed y to the 3rd, so that we know we have the correct term that we want in the problem. Definitely don't want to multiply those three together without a calculator, and you get negative 489,888. So that's the coefficient of this term. While this is something that's familiar, it's not what we're going to be talking about in math theory. We're going to go a little bit deeper, and we're going to use the binomial theorem for proving. So here it says, prove that the sum of all n choose k of x to the k is the same as x plus 1 to the n. So this is kind of a cool math fact. The idea here is that if I have a problem that, let's see, 1 plus n choose 1, x plus n choose 2, x squared plus all the way out to x to the n. This is the same as x plus 1 to the n. So this might feel familiar from our work with series in calculus. Now, for all of these, we're going to start with the binomial theorem here. And what we have here is we want to show, we know that this is true. And so what we see here, hopefully looking between this term and this one, is, oh, well, the difference here is that y is equal to 1. And that's pretty close. It's not going to quite get us where we want, but that's a good place to start. So, because the other thing is, you'll notice here is that x has the k, but then y has the k. So we're going to use the commutative property to say, well, this here, I can change my x and y within this parentheses, and I will change them also outside of the parentheses. So we still have the series k equals 0 of n, and n choose k. This parentheses is the same as 1 plus x, since we know that y and 1 we're going to set equal. Or you could even, if we want to take this a little bit slower, this is true, is the same as y to the n minus k, x to the k. All we're doing is using the commutative property. And now everything is nicely lined up, and we end up with y is equal to 1. As long as we do it to both sides, it's fine. So now we have the series of k equals 0 to n of n choose k, 1 to the n minus k, x to the k, is equal to 1 plus x to the n. Well, 1 to any power is 1, so we don't need to multiply by that. So we have the series from 0 to n of n choose k, x to the k, is equal to, and again, the commutative property, x plus 1 to the n. Now, we have proven, and this is an example of one where you can change both sides at once, because you started with something you knew was true and then did substitution. And that is the end of our proof, since we have what we are looking for. Now, I want to also look at a more complicated proof with combinations so that you get that additional practice. So here it says prove that k times n choose k is equal to n times n minus 1 choose k minus 1. So if we take 1 away from both of these, then these coefficients will switch. As always, we want to start with the one that has more terms. It's less simplified, there's just more to work with. So we want to start with this, which means that we want to end here. So what we want is k times n choose k, which I might even expand out a little bit more as n factorial over n minus k factorial times k factorial. And that just tells me, so I know that I'm done when I arrive at that point. So I'll start with n times n minus 1 choose k minus 1. And I'm going to start by expanding out using the factorial. So that's n times then n minus 1 factorial times n minus 1 minus k minus 1 factorial times k minus 1 factorial. And here's a really important fact about factorials. When I multiply these together, you get n times n minus 1 factorial. Well, n minus 1 factorial times n is n times n minus 1 times n minus 2 all the way down. So my numerator, when I simplify, is n factorial. And if you need a little convincing, you can write it out. n minus 1, n minus 2, 2 times 1. This is by definition n factorial. We'll just simplify the parentheses in the denominator here. We have n minus 1 minus k plus 1, distributing that negative, factorial, times k minus 1 factorial. The minus 1 and plus 1 here cancel out, and we're left with n minus k factorial and k minus 1 factorial. Now this is where it's super helpful to have what you want already written out over here. So I'm going to zoom out a little bit, give myself a little bit more space, is I know I want, and I have a lot of the parts already, right? I have my n factorial, I have my n minus k factorial, I want this to be k factorial. So I'm going to use the same skill that I just went over, and I know that k minus 1, in order to make it k factorial, I would multiply by k. This is now going to equal k factorial, which is what I want right here. However, if I multiply one side of a fraction by k, I also have to multiply the other side of the fraction by k. Oh, well look, that's just fine. That's going to give us this k out here. I'm going to use the commutative property to reorder it, and I end up with k times n factorial over n minus k factorial times k factorial, which is k times n choose k, which is our final answer. Please let me know if you have any questions about any of the proofs or anything that you've seen here. Please make sure that you're trying every problem, especially the proofs, checking your answers, and please be in contact with me if you're uncertain or just want to make sure that the proof that you're doing is complete. Look forward to hearing from you soon.